Dear students, in this video now we are going to discuss the remaining part of the Mossbauer spectroscopy. In our first video of the Mossbauer spectroscopy, we discussed about its working principle, we discussed about recoil energy and the Mossbauer effect, Doppler shift and the isomer shifts. Now here in this video we will discuss about nuclear splittings, that what are the quadrupole splittings and what are the nuclear magnetic splittings or hyperfine splittings. So the nuclear splitting, we can categorize the nuclear splitting, and basically there are two types of the splitting: quadrupole splitting, pole splitting and magnetic splitting. Okay, and magnetic splitting. So now we will discuss one by one that what are the quadrupole splittings and what are the magnetic splittings and what are the conditions for both these two types of the splitting. So first here now we are going to discuss about the quadrupole splitting. Okay, quadrupole splitting. So what is the quadrupole splitting? So the condition for quadrupole splitting condition is that the nuclear spin should always be greater than or equal to 1 by 2. That either it can be the ground state or it can be the excited. So here I present the nuclear spin. These are the nuclear spin. So the nuclear spin should always be greater than or equals to 1 by 2 for ground state or the electronic state. So this is one of the necessary condition for quadrupole splitting, to observe quadrupole splitting. Okay, so now here again I will take an example of iron. Here we will take an example of iron compound, that is iron 57. And you know that for iron its ground state spin is equals to 1 by 2 and its excited state spin is 3 by 2. What does it mean? It means that its ground state is degenerate. It's two-fold degenerate, and while its excited state is fourfold degenerate. Now what is mean by degeneracy here? And you know that degenerate states are those states if there are the two or more states of the quantum mechanical system and they are having the same energy, then these states are called as the degenerate states. So here the ground state is two-fold degenerate state, so its values are plus minus 1 by 2, and four-fold excited state has the value of plus minus 1 by 2 and plus minus 3 by 2. Now we can draw the excited and the ground state. So for ground state, here I have the ground state I and we know that it's the doubly degenerate and are two-fold degenerate state. So here I will draw two state and excited state, the four-fold degenerate. So here I will draw four different states. So there are the four states. So these are the minus 1 by 2 and plus 1 by 2, and these states are 3 by 2, 1 by 2, minus 1 by 2 and plus 1 by 2. Okay, now here is one more important thing about this state selection rule. So the selection rule here is delta I should be equal to 0 or plus minus 1. So only those transitions are allowed between the ground state and excited state of the nucleus, in which way the transition rule or the selection rule for the transition delta I should be equal to 0 and plus minus 1. So when electric field gradient is equal to 0, when electric field gradient is equal to 0, then only one transition is possible between excited state and ground state of these nuclear energy level. And so there is only one transition in the case of when electric field gradient is equal to 0. So the corresponding Mossbauer spectra, in the corresponding Mossbauer spectra, we observe only one signal. So the Mossbauer spectra will be like this one. So in other condition, let's suppose that now we have the electric field gradient not is equal. So in that case, now the ground state will be the same. It will be the twofold minus 1 by 2 and plus 1 by 2. But in the excited state, there will be the split in energy level. So there will be the split in energy levels, and there will be plus minus 1 by 2 and plus minus 3 by 2. So there will be the split in energy in the case of when there is the electric field gradient not is equal to electric field gradient not is equal to 0. So in this case, now we have not there will not be the only one transition. There will other transitions are also possible. So here in this case, we will observe the two transitions. First from here to here, and then second transition will be from ground state to the excited state. So now the spectrum will be like corresponding Mossbauer spectra will be like this one. So such a type of splitting, this split in energy level is known as the quadrupole splitting. It is called as quadrupole splitting. So this splitting occurs whenever electric field gradient not is equal to 0 and corresponding Mossbauer spectra, we observe the two or more signals. So the number of signals in the case of quadrupole splitting depends on the spin of ground state and excited state, or it depends on the degeneracy of excited states or the ground state. So if there are the more number of the ground states and excited states, then there will be the more than two transition, and the corresponding signals in the Mossbauer spectra will be more than two. But when we have the splitting like this one, then in that case we will observe the two signals instead of one signal in the case of Mossbauer spectra. One thing more to understand about these cases when electric field gradient either equal to 0 or it is not equal to 0. In both cases, that is without quadrupole splitting or with quadrupole splitting, uh, these cases are in the absence of magnetic field. We have not yet applied the magnetic field. So this quadrupole splitting is in the absence of magnetic field. Only condition for here the quadrupole splitting is the electric field gradient should not be equal to 0. Now I will tell you about the conditions, how the electric field gradient varies, that when it is equal to 0 or when it is not equal to 0. So here I will tell you about electric field gradient. Okay, so I can write it like electric field gradient. So I told you that as we have observed in our, I told you that if electric field gradient is equal to 0, then there will be only one signal, the Mossbauer spectra. So in that case, quadrupole splitting is absent. Or we can say that quadrupole splitting is not possible in the case of electric field gradient is equals to 0. And secondly, if electric field gradient not is equal to 0, then in that case quadrupole splitting will be present. Okay, so electric field gradients, what are the factors, necessary conditions for electric field gradients to be equals to 0 or not equal to 0? So electric field gradient, it depends on the symmetry. It depends on the symmetries, and symmetries are usually of two types. And here we have the ligand symmetry, and secondly we have second type of symmetry is the electronic symmetry. In any complex or in any kind of the compounds, we have the two types of the symmetry, ligand symmetry and the electronic symmetry. So the ligand symmetry, it can be the axial one, axial symmetry, or it can be the spherical symmetry. Okay, and same is the case for electronic symmetry. It can be the axial or it can be the spherical. Okay, now I will tell you that when the ligand and electronic symmetries are axial and when these are spherical. When both symmetries are spherical, then in that case, when both symmetries are spherical, in that case, electric field gradient is equal to 0. When it is equal to 0, when ligand symmetry and electronic symmetry both are spherical. Okay, and in that case, the quadrupole splitting is equal to 0, and correspondingly there will be the singlet state, or there will be only one signal in the Mossbauer spectra. So when the ligand symmetry is spherical and when it is axial. So for the ligand symmetry, it can be axial one and it can be the spherical. So when it is axial and when it is spherical. So it will be the spherical when the compound or your complex is the combination of tetrahedral coordination, or when there is the tetrahedral coordination, or your compound is purely tetrahedral and purely octahedral, then its ligand symmetry is the spherical symmetry. And it is axial. All other symmetries are axial one, other than octahedral and tetrahedral. So for axial symmetry, the axial ligand symmetry, it should not be in the octahedral combination and in tetrahedral combination. All other symmetries except octa and tetra are axial. Only the octa and tetrahedral symmetries are the spherical symmetry for the ligand symmetry. Okay, now we come to the electronic. So for electronic symmetries. So electronic symmetry, it can also be the axial one and it can be the spherical one. So again, to understand the axial and spherical one for the electronic symmetry, we take an example of iron. For iron, the electronic configuration is 4s2 and 3d6. If we take an isomers iron plus, then electronic combination is 4s0 and 3d6. So here the electronic configuration, there are the two cases. There is the case of low spin and there is the case of high spin. Okay, high spin. And for low spins, again, the d state further splits into the two states Eg and T2G. So the d state splits into the two states, and same in the case of high spin, there are the two states Eg and T2G. There are the Eg states, the doublet state, and T2G state, the triplets. So here we have 4s0 and 3d6. So for the case of low spin, here in the low spin case, we can fill the electronic states like this one. Two electron will be here, two electron here, and two electron here, and Eg state will remain empty state. So its electronic configuration can be written as T2G6 and Eg0. So there are 6 electron, all the 3d6 electron are in the T2G state. So here you can see that as all T2G states are the same and our levels are the same, and in the same way both Eg level are also same. How it is the same? Because both Eg levels are empty, so both Eg levels are the same and both all three T2G levels are also same. So here the filling of electron or the electronic configuration is spherical in this case. There is this is the spherically filled. We can say that energy levels are spherically filled. So this is the case of low spin. So the low spin allow the electron pairing. So there is the pairing of electron in case of low spin. So the first electron is filled in the T2G energy levels and then they pair itself. So the electrons come in pairs in the T2G energy level, one with spin up, other with spin up down, and then this is the spin up, spin down, and spin down. So all energy levels are filled by the electron pair with spin up state and with the spin down state. So this is the case of low spin and they are spherically filled. Why these are spherically filled? Because T2G energy level and Eg energy levels are the same. So all T2G are the same and both Eg are also same. So such a symmetry is called as the spherical symmetry in the case of electronic symmetry. When electrons are filled in the spherical manner, there is the spherical filling of the states, then such a symmetry is called as the spherical electronic symmetry. The spherical electronic symmetry. Now we come in the case of high spin. So when this is the case of high spin, so first electron with one spin will fill all the energy levels. So electron will go to first, it will fill the T2G states with a single electron and then they will come to the Eg energy level with single electron. So the remaining sixth electron with the spin down state will go to the T2G energy level. Now here you can see the filling is not, the electrons are not spherically filled. Why these are not spherically filled? Because here in T2G energy level you can see that this one energy level is the completely filled. Our electrons are paired with spin up and spin down state, but here we have in both these two states we have the single electron, while in the Eg we have the one electron, but Eg and T2G energy levels are not the same. So these are not spherically filled. So such a symmetry or such electronic configuration is known as axial filling of electron, or this electronic symmetry is known as the axial symmetry. So this is the axial symmetry. So spherical means that the electrons are symmetrically filled. Spherical symmetry means that electrons are electrons are symmetrically filled. That all energy levels are same. They are symmetrically filled. Okay. Here I will give you some more examples of the axial filling and spherical filling. So let's suppose we have more T. This one is the Eg level and this one is the T2G. And again I will draw this one Eg, and this one is the case of T2G. It can be Eg. Again there is the T2G, and here it is the Eg state, and this one is the T2G. Okay, so now I will tell you that what are the spherical filling and which one is the axial filling. So if the electrons are filled like this one, okay, all states have the one electron, then such a symmetry is the spherical, because the electrons are not symmetrically filled. All states are the same. T2G and Eg states are the same. Either electron filling can be like this one, it can be like this one. So again, the Eg states and T2G states are the same. Again, this is the case of spherical filling. So if the electrons fill like, either it can be like this one, it can be like this one. So both these are the empty, but these are paired. So again, this is electron, this is the spherical filling. So this is the spherical symmetry, but if the electron are like this one, these are like this one. Now this is the case of axial electronics, because in this case the filling of electron is not spherical. Now this is the different. So this is the spherical symmetry, this is the spherical symmetry. Electrons are symmetrically filled. Here the electrons are symmetrically filled, here also the electrons are symmetrically filled, but in this case the filling of electron is not symmetrical. That's why this is the axial electronic symmetry. Okay, now we will take an example of the compound iron H2O Cl3. So here we will see that either the quadrupole splitting is possible or not for this compound. If for this compound quadrupole splitting is possible or not. Okay, so now first we will check its ligand symmetry and its electronic symmetry of this compound. Okay, for ligand symmetry, its shape is the perfectly octahedral. Its symmetry is the octahedral, has the octahedral structure, so its ligand symmetry is the spherical. Its ligand symmetry is the spherical. But when it comes to the electronic symmetry, its iron is here. The iron is the iron 3 plus isomer, and so for iron 3 plus is has the 4s naught and 3d5 electronic configuration. So it is the case of it's the case of high spin. Why it is the case of high spin here? Because here the ligand is the water. So water is not so strong ligand for the pairing of electrons. So this is the case of high spin. So the filling of electron in this case will be like this one. So this is the EG state and this one is the T2G state. So in this case, the electron will be filled like this one. So here you can see that electron pairing is not possible in the case of high spin. So first a single electron goes to each energy level for high spin case. So again, you can see that these are spherically filled or symmetrically filled. Spherically filled, or you can say that the electron filling is symmetrical. So when electron filling is symmetrical, it means that its ligand symmetry and its electronic symmetry for both symmetries for these compounds are spherical. When both symmetries are spherical, what does it mean? It means that now in this case, electric field gradient is equal to 0. When electric field gradient equal to 0, then alternatively it means that quadrupole splitting is absent in this, or quadrupole splitting is absent, or either it is not possible. So corresponding Mossbauer spectra for this case will be the singlet one. We can observe only one signal because here there is only one transition between the ground state and excited state of nuclear energy level. So the spectrum will be like this one, and quadrupole splitting is 0 and electric field gradient is also equals to 0 because both symmetries of this compound, its ligand symmetry and its electronic symmetry, both are spherical. Okay, both are spherical. Electric field gradient is equal to 0. Quadrupole splitting is equal to 0. So now we take another example like iron 3n and plus 3. Okay, here we have the carbon iron plus 3. Okay, so for iron plus 3, the electronic configuration is 4s2 3d5. Here the ligand is the same. So this is the strong ligand. This one is the strong ligand, and it means that this is the case of low spin. Why it is the case of low spin? Because now the electron pairing is possible in this case. So here this one is the EG state and this is the T2G state of iron 3 plus. So here it is the case of low spin, so the electron will be filled in pair. So both these states will remain empty. So here you can see that the electrons are not spherically filled. When it is electrons are not spherically filled, it means that here is the electronic symmetry is the axial one. So when it is the axial symmetry, although ligand symmetry is also the octahedral. Ligand symmetry, the octahedral, but electronic symmetry is the axial. Electronic is axial one. So both electronic symmetries are not spherical. So this is the ligand, it is the spherical. It is octahedral, means that it is the spherical, but electronic symmetry is the axial one because electron filling is not, they are not spherically filled or symmetrically filled. So in this case we say that electric field gradient not is equal to 0. When electric field gradient here not equal to 0 because both symmetries are not spherical, so it means that here we can observe the quadrupole splitting. It is quadrupole splitting is present. Now the Mossbauer spectra will be different than the first case when the electric field gradient was equals to 0. So in this case, the Mossbauer spectra, instead of singlet, here we will observe the two signals in the Mossbauer spectra, and there will be the two transitions. Instead of one signal, there will be the two signals or the two transitions between the excited state and the ground state. So correspondingly, there will be the signal in the Mossbauer spectra. Now we will discuss the case of magnetic splitting. Magnetic splitting, or these are also called as the hyperfine splitting, and these are in presence of magnetic field, or when magnetic field is present. When magnetic field was absent, then in that case, when electric field gradient was equals to 0, electric field gradient was 0. So the ground state was doublet state, and that was equals to plus minus 1 by 2, and excited state was the four-fold degenerate state, plus minus 1 by 2 and plus minus 3 by 2. So this was the excited state, and so there in that case there was only one transition from the excited state to the ground state. So but when electric field gradient was not equal to 0, so in that case the ground state was the same, plus minus 1 by 2, but there was the split in the excited state. So this split in energy was like this one. So these states were plus minus 1 by 2 and plus minus 3 by 2. So in that case, there was two signals from ground states to the excited state. Okay, and so, but this was the case of when electric field gradient was not equal to 0. So this was the case of quadrupole splitting present, and so in this case, the quadrupole splitting was absent. Okay, but both cases was in absence of magnetic field, or when the magnetic field was equals to 0. So when we apply the magnetic field, the presence of magnetic field, there is the further splitting the energy levels. So the ground state will be the same, like there will be the two state plus 1 by 2 and minus 1 by 2, but there will be the further splitting in the case of excited state, and states will be like this one. There will be the further splitting of states, and so here states will be like this one, plus 3 by 2, plus 1 by 2, minus 1 by 2, and plus 1 by 2. Okay, so the states were minus 3 by 2. So here the selection rule, this is the in presence of field, and B field is present. And selection rule for transition, I already told you that it should be delta I should be equal to 0 or plus minus 1. So according to this transition rules, there the allowed transitions are for which the delta is 0 or plus minus 1. So one transition is from minus 1 by 2 to plus 3 by 2, because it's equal to minus 1. Difference of both states is 1 by 2 minus 3 by 2 is equal to minus 1. That is allowed transition. And then from minus plus 1 by 2 to plus 1 by 2, also possible transition, and then plus 1 by 2 to minus 1 by 2 is also possible transition. Now the second transition from this states from minus 1 by 2 to plus 1 by 2 is also possible transition. So this one is the possible transition, and then from minus 1 by 2 to 3 by 2. So all these transitions follow this one selection rule. So this is the case of magnetic splitting. So this is the case of magnetic splitting, or this is also called as the hyperfine splitting. So in that case, in the case of electric field gradient is equals to 0, we have only one signal and corresponding Mossbauer spectra is like this one. And in the quadrupole splitting, when electric field gradient is equal to 0, then corresponding Mossbauer spectra will be like this one. Will be the two signals. But when magnetic field is present and electric field gradient is equal to not equal to 0, then we have the spectrum like now we have the 6 signal. So now the spectrum will be like this one. So this is the corresponding Mossbauer spectra for magnetic splitting. This is the Mossbauer spectra for quadrupole splitting, and this one is the for electric field gradient equals to 0 in absence of quadrupole splitting. So here we will do the splitting for the nickel. For nickel, the excited spin state is the 5/2 and its the ground spin is 3/2. So it means that its excited state is the 6-fold degenerate because it has the state plus minus 5/2, plus minus 3/2 and plus minus 1/2. While the ground state is the 4-fold degenerate because states are plus minus 3/2 and plus minus 1/2. Now we draw the two cases here. The electric field gradient is equals to 0. For electric field gradient is equal to 0. Here the ground state will be like this one. It is 4-fold degenerate. So this is the plus minus 3/2. These are plus minus 3/2 plus minus 1/2. So this is the ground spin states, and for excited spin state it is 4-fold degenerate, 6-fold degenerate, 5 and 6. So this one is the plus minus 5/2 plus minus 3/2 and plus minus 1/2. So these are the excited spin state. So when electric field gradient is equals to 0, so there only one transition, and the corresponding Mossbauer spectra for this case will be like this one. That is, here we observe only one signal. That is only one signal when electric field gradient is 0, and quadrupole splitting, that it is absent here. So now we goes to the case when quadrupole splitting is present. When quadrupole splitting is present, it means that now electric field gradient not equals to 0. When it is not equal to 0, then there is the split in the ground state and excited state as well. So ground state, it will be the split like this one. These are the ground states. So these two states are plus minus 3/2, plus minus 3/2, and these are plus minus 1/2. So in the same way, the split in the excited state, there will be the split in excited state. So these states, this is the split. So these states are plus minus 1/2, plus minus 3/2, and plus minus 5/2. Now the transition rule or selection rule, you know that this one is equal to 0 plus minus 1. So according to this transition rule, now possible transition between excited state and ground state are, that is from it's possible from here to here, and then second transition from this one, and other possible transitions are from minus 3/2, minus 3/2, and other ones are possible transitions are from plus 1/2 to minus 3 by 2 and plus 1 by 2 minus 1 by 2. So here are the 5 signals. So instead of two transitions, instead of two signals, like in the previous case of iron, here we have the 5 signal in the Mossbauer spectra. In the case of nickel, when electric field gradient not is equal to 0, that is quadrupole splitting is present. When quadrupole splitting is present, this means that no Mossbauer spectra that is recorded. It's like this one. So there will be the 5 signals. 5 signals observed in the case of Mossbauer spectra. So here electric field gradient is 0. So both these are the cases when B field is equal to 0, or we can say that when magnetic field is equal to 0. So now we will go to the what happened to the nickel, the Mossbauer spectrum of the nickel in case of the presence of magnetic field. The presence of B field. The presence of B field or magnetic field. So when magnetic field is present, then there is the magnetic splitting or hyperfine splitting for nickel. Okay. Now splitting will be like this one. So the ground state here, in the case of ground state, there will be the further splitting. There will be the 4 energy split, further split into the 4 different energy levels. Okay, these are the energy levels: plus 3 by 2, plus 1 by 2, and these are minus 1 by 2 and plus 1 by 2. So in the same way, there is the splitting in the excited spin state nucleus, and there will be the 6 states. There will be the further splitting of these 6 states. This one. Okay, and these states will be the plus 5 by 2, plus 3 by 2, plus 1 by 2, and then minus 1 by 2, minus 3 by 2, and minus 5 by 2. Okay, now according to the transition rule, selection rule, delta I is 0 plus minus 1. So the possible transition in this case is first is from plus 3 by 2 to plus 5 by 2. And second one is plus 3 by 2 to 3 by 2, and from 3 by 2 to 1 by 2. So these are the possible transition. Other possible transitions are from plus 1 by 2 plus 3 by 2, and then from plus 1 by 2 to 1 by 2, and then from plus 1 by 2 to minus 1 by 2. And others are from plus 1 by 2, plus 1 by 2, minus 1 by 2, plus 1 by 2, and then from plus 1 by 2 to minus 1 by 2, and from here 3 by 2. And then other are from minus 1 by 2, from minus 1 by 2 it will be possible to 3 by 2, and then from minus 1 by 2 it will be equal to the 1 by 2, and then from 1 by 2 minus 1 by 2. These are the possible transitions. So there are the possible transition or 12 transitions. So in the case of hyperfine splitting, in the case of nickel, there will be the 12 signal in the Mossbauer spectrum. So we can say that when electric field gradient is absent, so there is only one signal. When electric field gradient electric field gradient not equal to 0, then there was the 5 signal. And so this was in the case of B is equal to 0. When B not equal to 0, then we have 12 signal. Okay, this was all about the quadrupole splittings and the hyperfine or magnetic splitting. So now here in this figure, I have summarized all types of the splittings. So when here you can see that when there is unperturbed states and there is no magnetic field, then our electric field gradient is equal to 0. Then here we have only one signal, and Mossbauer spectra will be like this one. And so when there is the isomer shift, so then there will be the shift in energy. Here you can see that there will be the some shift in energy of the ground state and excited state. So our Mossbauer spectra will shift a little bit by unperturbed state. And in the case of quadrupole splitting, here you will absorb the two signals. And in the case of magnetic splitting, here there will be the further splitting of the states, and here we will observe more than two signals, or because there is a further splitting of states as in the presence of magnetic field. So this was all about the splitting in the case of nuclear splitting and about Mossbauer spectroscopy.